Hello everyone, we are Team ME13 and ECE 2114. This is a joint mechanical engineering and electrical and computer engineering project. My name is Chris and, along with Jared and Mohammed, focus on the electrical aspects of the project while Yusuf worked on the mechanical aspects. Our sponsor is Collins Aerospace and our goal is to improve the power supply efficiency of aircraft applications by switching from the standard silicon-based transistor to the gallium nitride based transistor. We went with a two-prong approach to successfully complete this project. First, we chose a GaN FET that met our sponsor's requirements and designed a 4-layer printed circuit board to evaluate our GaN transistor performance. The first layer served as a power plane for the input voltage and output voltage and contained all the components along with most of the traces. The second layer served primarily as a ground plane. The third layer's primary function was to connect the GaN FETs to the output inductor, and the fourth layer's primary function was to finish tracing any connections we were unable to perform on the first layer. Second, we ordered a buck converter evaluation board that used our chosen GaN transistor and a comparable silicon converter evaluation board. We performed tests in the laboratory with the same parameters for each: equal input voltage, function generator duty cycle, and switching frequency. This would allow us to compare and contrast the performance between each type of transistor with a focus on output voltage ripple, transistor switching characteristics, overall circuit heat dissipation, and efficiency.
Hello, my name is Mohammed Shabazz. I'll be expanding on laboratory testing. We start off with the initial turn-on test. The one on the left is the GaN board, the one on the right is the silicon board. Then we obtain ripple for each board. As you can see, the GaN on the left has significantly more ripple than the silicon on the right. Then we obtain VDS waveform for each board. The images on the top is the general waveform, and images on the bottom is the overshoot, with the GaN board having 4.8 volt overshoot and the silicon board having 10.4 volt overshoot. We then moved on to obtaining VDS waveform for each board. The GaN board has two transistors, so we obtained VDS and VGS waveforms for the second transistor. We also obtained thermal imaging to highlight the hottest parts of the board during operation. We are performing further testing in lab to provide thorough final report. From testing this board, we decided to include test points on our PCB to obtain VGS and VDS waveforms safely. Our ME partner will be running ANTHES simulation for further thermal analysis.
Our PCB design contains the same components as the GS61008P-EV-BHF evaluation board, with 8 additional test points and a Kelvin sense resistor. 7 of the additional test points are placed at each of the transistor's gate, source, and drain, which allowed us to capture the gate-to-source voltage and gate-to-drain voltage waveforms for both transistors. A critical design decision we made was to place each pair of the test points used for capturing a particular waveform strategically close to one another. This results in more accurate readings, as when test points are too far apart, their parasitics will be too high and reduce the accuracy of the data. The last additional test point and the Kelvin sense resistor were included to measure the current. The Kelvin sense resistor has a low resistance and is connected in series with its big leads to carry current, while test pads can be connected to the small leads for measuring the voltage across the sense resistor. By not interrupting the current path of the loop of wire, the performance of the circuit is preserved during the measurement.
Here's our ANSYS simulations where we run ANSYS simulations for thermal analysis. I started the ANSYS simulations with a simple model here on the left picture, where the board is a simple rectangle block and all the components are simple rectangle blocks sitting on the surface of the board. Then here on the right picture we have a more realistic board with all the components details, like the board have the holes. And for example, here we have on the right picture the inductor with all its details, but on the left picture we have the inductor as a simple rectangle block. Also here on the left picture we have the gate driver touching the board directly, but on the right picture in reality there we have 16 pins connecting the gate driver and the board. In result, on both models, the transistors had the highest temperatures as expected, since each transistor has a power dissipation of 1 watt, so both of them have 2 watts of power dissipation, where the inductor only has 0.9 watts and the gate driver only has 0.04 watts. Overall, the more accurate model had a 2 degrees Celsius higher average temperature distribution than the simple model. Our remaining work involves testing the PCB that we ordered and will arrive towards the end of April. We will test its temperature distribution and compare it with the ANSYS simulations result. Finally, we would like to thank UConn School of Engineering and Collins Aerospace. Also, we would like to thank our sponsors, Mr. Bill and Mr. Tom, and our faculty advisors, Dr. Park and Dr. Chu, for their help during this project.